randomly generate the values of x1, x2. Now, the solution will be generated using two parameters, that is the pitch adjusting rate, harmony memory consideration rate. Based on these parameters, new solutions will be generated. Now, how do the musicians generate the new music? Either they take the memory, what is the music they have already developed, so they make combination of that, so that a new harmony can be generated, or generate a new music or new bandwidth for a particular instrumental music. So now so in the step 3, we create a new harmony. New harmony will be x prime equal to x1 prime, x2 prime up to xn prime, generated based on 3 rules, that is the harmony consideration, or pitch adjustment, or random selection. Harmony consideration is also known as improvisation, where we will generate a new music based on the old memory. So x1 prime, that is the new value, will be from that old value, right? From that old values, anyone from that old value. Already you have say x1, you have x1, x2, x2 up to x1 HMS. So you can choose anyone from that with the probability harmony memory consideration rate. You can choose any value from that column. For x1 prime, you can choose any value from the first column. Similarly, for x2, for the new x2 value, we can choose from the x2 values with a probability, that is HMCR, or harmony memory consideration rate. Based on that, you can choose from that old, or you can create a new one with a probability or new value. X1 prime will be new one within the range of x1 xi values. So you can generate a new value with a probability that 1 minus HMCR. With the probability HMCR, you generate a probability. If the probability equal to the or less than equal to HMCR, then you use that anyone from the old values. Or if it is more than HMCR, then you create any value between any. So either with HMCR, you choose any value from that old one, or 1 minus HMCR, you choose a new value. Now, once a value is chosen from that column for a new x1 value or xi prime from xi column, if it is chosen with the probability HMCR, or a new value with the probability 1 minus HMCR, this will be either pitch adjusted or not. So for pitch adjustment, whether that what is the value that you have chosen that needs any pitch adjustment or not, that can be given by a probability. So pitch adjustment decision for xi prime, it is yes with probability pitch adjustment rate with a PR. So it does not require any pitch adjustment with probability 1 minus PR. If it is so if the value is 1 minus PR, then nothing is to be done. If pitch adjustment decision variable for xi prime is yes, then xi prime is replaced with this xi prime equal to x1 xi prime plus or minus random into BW, where BW is known as the bandwidth. So this rand is nothing but a random number between 0 to 1. So now this pitch adjustment rate is dynamically changed from one generation to another generation. Okay, so the bandwidth in a generation will be given by an equation, bandwidth BW max multiplied by e to the power c into gn, where gn is the generation number or iteration number. This bandwidth is generated by this c is given by relation ln BW mean by BW max divided by number of iterations. So it is a very simple algorithm. What we do, initially generate a population pool. Each column x1, x2, x3, all these variables to generate a population pool of size HMS, that is the harmony memory size. Then take one row, take one value, that is x1 prime, whether x1 prime is to be selected from that x1 column, any value from that x1 column with a probability HMCR. It will be new value with a probability 1 minus HMCR. So whatever may be the case, if you select one, then whether it needs pitch adjustment rate or not, that decision you have to take by generating a probability. If the probability is PR, then the decision may be to change. If the probability is 1 minus 1, so decision is to not to change the pitch. If the pitch adjustment is to be made, then pitch adjustment is made, then this pitch adjustment is given by this relation. So new value of xi prime will be xi prime plus or minus rand into BW. Now BW is the bandwidth. Bandwidth is generated. Bandwidth is changing from one generation to another generation using this relation. Now here the C is given by this relation, and Gn is the generation number, and is the number of iteration. But this pitch adjustment rate also changes from generation to generation. It is a dynamic. It is not a constant throughout the solution using this relation. Now once this new harmony is generated, it may have a better solution than the worst solution. So the worst solution is replaced by the new solution. If it is not good enough, then it will be rejected. A new solution is to be generated. So this step will continue till you get the best values. Now again we take the Raster Angle function with the 2 dimensions. Then harmony memory size you take 8. Harmony memory consideration rate is 0.95. You see here harmony memory consideration rate. You choose a value from the old memory or from the old values for each variable with 95% or 95% probability that you choose from the new old values. Now there is only 5% you choose a new value for that within the range of the variable range of xi. So similarly, pitch adjustment rate, whether you require pitch adjustment or not, so that is 25% is given. So if the pitch adjustment rate, so 25% of the new generated values will need the pitch adjustment, or 75% will not need the pitch adjustment. So all these HMCR and PAR are used only to get some variation in the solution, only to get the diversity in the solution, so that new solution will be superior than the old solution. Then the bandwidth is given, for the initial bandwidth is given by this value. Number of iteration is 4000. So you look at the initial generation like this. So initially randomly generated x1, x2, fx is the function evaluated using this equation. Now, in the next solution, x1 prime will be any value from these existing values with a probability HMCR, right? So 95% probability that your new x1 prime will be from this column, any value from this column, that is 95% chance. Or it will be a mu1 within the range of x1. So that I have told you that in this case, Raster function x1 and x2 lies between minus 5.122 to plus 5.12. So it will be from a new value. So that is the probability is 5%. Then the whether if you select one, it reach pitch requirement, pitch adjustment or not. So that probability is 25%. So 25% of the values that is selected, that goes for the pitch adjustment. Otherwise, there is no pitch adjustment. So these are the equations that will be used, and you can solve this problem easily. Now let us see a MATLAB program for solving harmony search. You see, here you can see the best solution. So best solution is this one, and this is the best cost. So we're not. It needs some more iteration to get the value of x1 equal to 0, x2 equal to 0, and fx equal to 0. It needs some more iteration. You see, for the best solution, position values, we got it is almost 0, but not exactly equal to 0. So it needs some more iteration. In the previous examples, you have what I have shown. It was getting nearly equal to 0 for fx value and x values of x1 and x2. But here, here it needs some more iterations, and definitely will get. Okay. Data. Next is and this is the convergence curve that we get. Now in optimization problem, we come across a lot of constraints. These are to be handled. That is, the constant can be handled using 4 types of rules. One is the rejection of solution violating the constant. Suppose you have this is the solution. Now this solution 1 is one of the best solution, and a solution 4 is violating the constant. So what are the solutions which are not violating the constant that we put in this box? Solution 1, 2, 3, and solution 4 is violating the constant. So that was set aside. Now, first method, that is the rejection of solution violating the constants. Here, when a solution is violating the constants, you reject that solution and get a new solution which is not violating the solution. In doing so, what will happen? A large number of solutions will be rejected, and it takes a lot of time to get the solution which will meet the constant requirements. You look at here, the optimal solution is 1, but solution 4 is very close to solution 1, because and it may in the next iteration or 1 or 2 iteration, it may approach near to 1. You see, solution 2 is not constrainting not violating any constant, but quite away from the optimal solution, and it may reach this may reach towards this or this value. It may take longer time, but solution 4, which is nearer to 1, so it may reach in less computational effort or less time, it may reach to 1 or optimal solution. But as simply it is violating the solution, we are rejecting. So in that case, a good solution which has the potential of giving good solution, that may be rejected. If you use the rejection of solution when violating the constant, if you use that method, then lot of solutions will be rejected. We will be left with a small set of solution. We may not get good solution. So rejection of solution by violating the constants is not treated as a good strategy. And another method is that repair of infeasible solution. The solution which are violating the constants, you repair that solution so that it will come to the feasible region. Then the repair strategy differs from problem to problem. So there is no generalized repair strategy. So third strategy is apply penalty to the solution violating the constant. You put a very large penalty into the objective function when you violate the solution. So this is quite practicable solution, and in fact we do it in linear programming. We might have come across the Big M method. In the Big M method, what we do when the artificial variables not equal to 0, you put a very large penalty in the objective function. We put m into r, where m is a very big number and r is a artificial variable. So when this r is not equal to 0, we put a very large penalty in the objective function. So this is the penalty of putting or penalty for violating the solution. Then fourth, so this is a practicable solution, and also the fourth method that I apply some rules to rank the available solution, which is found to be one of the good solution, and we rank the solution based on the violation of the constant. So now basically we use the Deb's rule. Deb's rule says that out of two solutions, if both are feasible, then the one with minimum value of objective function is given higher priority. If one of the two solutions is feasible and the other one is infeasible, then the feasible solution is given higher priority. If both the solutions are infeasible, then the one violating less number of constants is given higher priority. If both solutions are infeasible and have same number of constant violations, then the one with the lower objective function is given the higher priority. So these are the four rules that is adopted while prioritizing the solution based on the violation of the constraints. So we define a constant fitness priority based ranking. Now fx is equal to 1 if this is for the less than equal to constant, that is 0, and 1 minus gix by gmax by x if gx is greater than 4. Then similarly for equality constants. So now for the constant fitness priority based ranking, we calculate the constant fitness. That is, we calculate depending on the violation of the constant using this equation 4 and 5, and you go on giving the weightage for each violation and multiplied by the FIX, then summation of the weights will be equal to 0. So we develop a constant fitness priority function. Now all these constant fitness priority function, this if there is these values, this f con x, that constant fitness priority function, that will be between 0 to 1. So when there is no constant is violation, then this assumes a value of fx will be equal to 0. If there is violation, constants are violated, then it will be equal to 0. So now now all the solutions that we generate, these will be arranged in the descending order of constant this f con x. So 1, if it approaches 1 means there is no constant violation, so that is the best solution. If it value is somewhat less, then there is a little violation. So we arrange these or prioritize the solutions based on the constant priority function, then the solution will be obtained. So this is how do we handle with the constant optimization. This constant optimization has been this priority based constant fitness priority based ranking that has been can be incorporated with the basic algorithm, whether it is a SOPT algorithm or PSO algorithm or HS algorithm. It can be incorporated with this. Then we can find or handle the constant in a better manner. So mostly what you do when the analytical solutions are existing, we use the analytical solutions for optimization, or when if it is not existing, you use the numerical method for numerical methods for getting the objective function. And sometimes you use some design of experiment approaches like Taguchi method or factorial designs, fractional factorial and full factorial design, or response surface methodology to conduct the experiment and develop the empirical equations. So the empirical equations mostly people use the response surface methodology because it is one of the easy way of getting the functional relation. So either you use the central composite design or the box Van design. These are the two ways of getting the equation using the response surface methodology. One interesting thing is that if you use the box Van method, then the levels of the variable will be always in three levels. But if you use the response surface, central composite design, you can have more number of labels for the variables. So these are the methods we use we find the empirical relation for solving the problems. Now come to one example here. That is the turning of titanium alloy under minimum quantity lubrication. So this case study is taken from reference 19. Now titanium grade 2 round bars having 150 mm axial length and 52 mm diameter is used as the workpiece material. Turning test is performed on high precision CNC turning center with the Siemens control. Sieben insert having nose radius of 0.4 mm is selected as the tool. Now a fresh tool and 75 mm of cutting length were maintained for each experiment to avoid the effect of tool wear on the given responses. So this is the setup given, and here what we use is the minimum quantity lubrication. Um, so minimum quantity lubrication is used. Then here the variables is used is the cutting speed, feed, approach angle of the tool, then the output is the cutting force, flank wear, and surface roughness. And the design is made based on the box Vanken design. Box Vanken design is used for conducting this experiment. Then cutting force, flank wear, surface roughness is to be found out. You see, the equation are developed. These are empirical relation that has been relations have been developed. This is the cutting force for FC. So this is the cutting speed, feed, and the approach angle in terms of cutting speed, feed, and the approach angle. This equation has been cutting force equation has been developed. Similarly, for the flank wear equation has been developed, and for the surface roughness equation has been developed. Now, this has been solved using particle swarm optimization. Using particle swarm optimization, cutting speed, feed, approach angle. These are the cutting speed, feed, and depth of approach angle has been found out. Then, in that case, cutting force, flank wear, and surface roughness was found. These are the values found. Now, using this optimal parameter setting, one experiment has been conducted to know whether this optimal parameter setting is good or not. So some test has been made. So another experiment has been conducted taking the optimal parameter setting 200, 0.1 and 90, and the cutting force was found 132.45, whereas the algorithm gives PSO algorithm gives 132.52. Flank wear is 0.31, and experiment confirmation experiment gives 0.34, and surface roughness 1.53, and the confirmation experiment gives 0.56. So this is one example where we have used the optimization. Now, in the particle swarm optimization, the major problem arises is that if you use the normal particle swarm optimization, the velocity values go on reducing as the iteration proceeds. So if the velocity values approaches towards zero, then there will not be any diversity in the solution, or we can say it will be trapped at the solution is trapped. You cannot move further. This frequently occurs with PSO. When you compare PSO with genetic algorithm, genetic algorithm takes long time for the solution. Same type of problem, it takes long time for the solution, but it gives good solution. But particle swarm optimization takes less number of iteration. If the solution is found, it is okay. If the solution is not found, then it will be trapped at the local optima. Whatever you do, you will not get at the good solution. This is the problem with particle swarm optimization. So what you have to do, either you make some strategy to get rid of this trapping at the local optima, or another method that has been developed that is known as quantum particle swarm optimization, where the velocity concept has been removed and the changes have been based on the quantum theory. The details will take a long time because the lot of equations are there, but it is based on the quantum theory, and this velocity has been what is used in the normal particle swarm operation that has been avoided. So this quantum particle swarm optimization has been applied to optimization of compressive strength in fused deposition modeling. Fused deposition modeling is one of the rapid prototyping processes or one of the additive manufacturing processes. Now, here what we have done, the compressive, for testing the compressive strength, samples were prepared, 3D samples were prepared by CATIA 5, that is the, then this this file is saved in .htl file, then it has been given to the FDM machine, that is Portus 400 machine from Stratasys. The machine has its own software that is known as the Insight software. What the software does, it slices down the solid model. It slices down. So in FDM there is a so in the FDM the model material that comes through a nozzle and spreads over the surface, which was cut down by the Insight software. So one layer of material can be placed, then another layer of the material, then another layer of the material, and the material comes out from the nozzle in the semi-molten state. So two layers will be fused together or bonded together, so that a solid model can be built. And the material that here used was the ABS plastic, acrylonitrile butadiene styrene plastic material that is used. So skewer prism specimen parts of 10 mm, 10 mm and 30 mm parts have been used, fabricated using FDM vintage AC machine. Now the compressive strength is measured using the using a ISO standard ISO 604 1973. Based on that, these parts have been made, and the samples were tested for the compressive strength. It is tested on a Instron 1195 series machine with a crosshead speed of 2 mm per minute. Okay, so now the parameters that we considered here is the layer thickness, the thickness of the layer. The thickness of the layer depends on the type of nozzle or the diameter of the nozzle that is used. So there are three levels are possible, that is 0.127, 0.178 and 0.254. So layer thickness will be three levels. Similarly, sample orientation. How to orient the sample in the machine? So sample orientation with respect to the x-axis, the machine, how to orient the sample. So the orientation can be at 0 angle, that is parallel with the machine, or it can be at 15 degree, or it can be at 30 degree. Then the raster angle, the nozzle, when the material comes out from the nozzle, it gives the H mark, or material is filled in HS mark. So the that is now at you can give in 0 angle, or you can give it 30 angle, or you can give in 60 angle. So hedging will be 60 or 30 or 0. Then the raster width of each filament that is coming out from the nozzle. So the raster width at three levels, 0.4064, 0.4564, 0.5064. Then the air gap. Air gap is the distance between two rasters, that is known as the air gap. Air gap can be 0 or 0.004 or 0.008. Now, based on a response surface methodology has been adopted for conducting the experiment. Here we have used the face-centered central composite design. If you use the face-centered central composite design, then the number of levels for all the factors will be 3 only. Okay, so or the axial point lies on the face of the cube. So here we use the face-centered central composite design. Then the natural variables are converted into the coded variables using this relation. This is for the codification of the variables, so that all the variables will be between -1 to 0, 1. -1 means low level, 0 means medium level, and 1 means high level. So this can be coded using this equation. Okay, coding is essential, and it is there is no generalized formula for coding. You have to develop the coding for your own um, experiment. So now these are the experiments that we these are the experimental results. That is 5 parameters that we consider: layer thickness, sample orientation, raster angle, raster width, and air gap. So all these 5 variables, and this is the compressive strength we got using the all the samples were prepared taking um, these parametric levels, and the compressive strength is measured using the instrument machine. So now an equation has been developed, empirical equation has been developed. The variables will be within these limits. Now this has been solved using swarm optimization or quantum wave particle swarm optimization. So maximum compressive strength we got is 17.451 MPa. Then the optimum factor setting is the layer thickness is 0.254, orientation 0.036 degree, raster angle is 59.44 degree, raster width is 0.422, and air gap is 0.00026. So these are the things that we got. Then come to another example where the abrasive jet machining is used. Abrasive jet machining, everybody knows there is a abrasive particles that impinge on the workpiece. Then we do the machining. Now here the variables considered are the mass flow rate of abrasive particles, that is MA, mean radius of abrasive particle RM, and velocity of the abrasive particle VA. So the model is for material removal rate. This is the equation. You remember, this is an analytical equation or developed from the physics of the method. So, and the similarly for the surface roughness, this is the equation that we find. Then the surface roughness is given. This equation is greater than or equal to 0. So range of the variables for 3 variables: MA, mass flow rate of abrasive particles, that will be within this range. Then the radius of abrasive particles, mean radius of the abrasive particles, that is the range given, and the velocity of abrasive particles, that is the range given. So density of the abrasive particles, you see density is used here, rho A, of abrasive particle, that is for alumina is used as an abrasive particle. So the density is given, and proportion of abrasive particles effectively participating in the machining, that is eta A. So this is what in the equation it is used, that is taken 0.7, and flow stress of the work material is glass. So sigma FW, so that is 5000 MPa. Allowable surface roughness value is 0.8 micron. So now this problem has been solved using uh, so these are now you see there are four uh, methods or four techniques have been used, that is genetic algorithm, simulated annealing, TLBO, teaching learning based algorithm, and SOPT. Now, so these are the parameters. For mass flow rate, all the algorithms gave almost the same. Then for RM, all the algorithms give the same, and for velocity of the average particles, these are different by algorithm. You should look at the material removal rate. Material removal rate, GA gives 8.236 and SA gives 8.257, TLBO gives 8.9769 and SOPT gives 8.258. Surface roughness, you see TLBO gives 0.846 but SOPT gives 0.799. But the surface roughness that is tolerated is 0.8 micron. Allowable surface roughness value is 0.8. So see that TLBO violates the surface roughness constraint. So this is the program which will give you the solution using the SOPT algorithm. Now this will take a long time for solution. So let it be solved and we will discuss some other things. Similarly, turning of carbon fiber reinforced plastic composites, that has been solved using TLBO. Here the tool used is the single point HS cutting tool. Then CF is the cutting force, RA is the surface roughness, MRA is the material removal rate, and the parameters that is used is the spindle speed, feed rate, depth of cut, and the fiber orientation. Fiber orientation in the carbon fiber reinforced plastics. And the equations have been developed. All these are multiplicative or power equations for all the outputs. Now, these equations have been developed based on the experimental design and empirical models. Okay, so then you look at the comparison between the genetic algorithm and teaching learning based algorithm. You see, for the cutting force, genetic algorithm is 2.60, whereas cutting force in TLBO is 2.5686. And surface roughness, genetic algorithm is 6.34 and here it is 5.09. Material removal rate, you see, genetic algorithm gives 4366.52 and whereas TLBO gives 4465. So so still that is continuing, not solved yet. So here in this problem, TLBO is superior to genetic algorithm compared to all the aspects. Now the question is that when you have single objective, we have solved or have seen that several case studies, these single objective functions are working fine and gives good results. Yes, we got the solution. We got the so now see the solution. By SOPT, you see the MRR 8.258 by SOPT. So this is the value we got. Now here it is coming minus because material removal rate is maximized, and this program is written for minimization, so we multiplied by -1 the objective function. Okay, so 8.25 we got. And this is the constant, whether you are validating the constant that is or not, that is given, and these are the parametric values. So we have come to various types of problems that can be solved using different algorithms. Now come to multi-objective optimization. In the multi-objective optimization, we have more than one objective function, and all the objective functions are to be solved simultaneously, or all the objective functions must be met simultaneously. So in that case, it is difficult to get a single solution. You can get a single solution if all the objectives, suppose you have two objectives, F1 and F2. You can get a single solution if you multiply F1 by W1, so you can have W1 into F1 plus W2 into F2, then you can have a single solution, or both the objectives, you can take the weighted equivalent objective function, then you can get a single solution. But when you take the weighted function, what happens? The F1 is in different scale and F2 is in different scale. So that will be scaling problem, and it may not give good solution if F1 value is in large numbers and F2 value is in small numbers, then only in the solution F1 value will be reflected. So both the values cannot be reflected. So that is the problem with the weighted functions. That's why what do people do when there are multiple objectives? We generate the non-dominated solutions or best solutions or the Pareto solutions. Non-dominated solution means if you have two objectives, a solution which is superior to another, you compare the solutions. If a solution is superior to other solution in all respects, in all objective function, then it is a dominated non-dominated solution, or a solution which will be superior at least in one objective function, then also it is called a non-dominated solution. So we find out the non-dominated solution. So this non-dominated solution will form a Pareto solution, or it will give a Pareto set. So after the solution of multi-objective optimization problem, you get a set of solution instead of a single solution. You get a set of solution. All the set of solutions are non-dominated solution and all are good solution. So anyone can be chosen. It depends on how the decision maker want to choose. So now in multi-objective solution, the example is given for the particle swarm optimization. It is similar to the particle swarm optimization. Only thing what you do in the particle swarm optimization, what you use the G best solution, that is the global best solution. For finding out the global best solution, what you do, we keep the solution, the non-dominated solutions in another archive that is known as external archive. So from the external archive, the top 10% of that solution will be treated as the global best solution to be used in the equation. That is the velocity change equation and the velocity updation equation and the position updation equation. Only top 10% that is to be used from the external archive as the global best solution. And this problem is with all the algorithms, they adopt a similar thing, whether it is genetic algorithm or TLVO or whatever the solutions that we find. Then you check all these solution and find out the non-dominated solution and put that non-dominated solution in the archive, external archive. So from the external archive, you bring it for necessary changes. What you do in the solution. In the genetic algorithm, PSO, TLVO, in HS, in all the multi-objective equation, this is the main thing that we do. Then another thing, that external archive that will be filled. So what you do, time to time when you get good solutions, so some of the solutions which are not better solutions, these are to be removed to maintain the external archive fixed. And another thing, we we arrange all the solutions from the, we arrange all the all the solution. We arrange all the solution in the external archive in a descending order of the crowding distance. The crowding distance will give you what is the diversity existing among the solution. So the crowding distance is this. That is, so for example, this is the, we will find the crowding distance for this. This is for the, so the crowding distance will be given by difference, that is f1k plus 1 for two solutions, f1k plus 1 minus fk minus 1 divided by f max minus f min. So this will give the crowding distance. If the crowding distance is more, so there are more diverse solutions. So these are, so we arrange the solution based on this crowding distance. Now we take from this crowding distance some of the solutions and from the top 10% that will be used from the external archive for making modification in the actual values, particularly in PSO, the velocity updation and the position updation. We need the G-based solutions we use. Similarly, in GA, we under the best solution from the external archive. We take the good solutions in. So same way we do, and this has been applied to an electrical discharge machining processes. Here the workpiece used is the Inconel alloy 718, a nickel chromium based alloy. Then the tools that we used are brass, then copper and the graphite. These are the diameter of the tool is 13.5 Then experiment has been conducted for 30 minutes. All the then the output that we want is the material removal rate, tool wear rate, electrode wear ratio, and the radial overcut. And the surface roughness. So experiments have been conducted as per response surface methodology. Experiments have been conducted as per the response surface methodology, and there are 54 experiments have been conducted. Now, then after this experiment, empirical relation in the coded form it is found for material removal rate, electrode wear rate, for surface roughness, and radial overcut. Then there are 4 objectives. Sometimes we are not interested for simultaneous optimization of all the 4 objectives. So 2 objectives are to be have been taken at a time. That is the maximize RR, minimize EWR, electrode wear ratio, subject to surface roughness constant that is less than 6.8, radial overcut less than equal to 0.03. Similarly, another problem taken, maximize MRR, minimize the surface roughness, subject to EWR, this and radial. Similarly, 6 problems have been found out, and all these problems have been solved. So for the multiple objectives, material removal rate and EWR, the best parametric condition that has been found out, and the objective function is the material removal rate is 54.11 and EWR, electrode wear ratio is 8.98. So for all the these are the samples. Actually, we got the Pareto set, and out of this, some of have been represented here. So this is what the Pareto set that we will find. This is for the material removal rate and EWR. So all the solutions are non-dominated solution and good solutions, and that can be found out. So this is the one example given how to get the Pareto set. Okay, for 2 functions, a Pareto set can be found out, and the solution you can see. Okay, so these are the way we do. So we have discussed in nutshell the different types of algorithms that is being used as single objective type, multi-objective type, how to handle the constraints, and the various applications that also we have discussed. So there is a tremendous scope that you will use these new algorithms for optimizing the manufacturing processes. Every day, new algorithm is being proposed, and we have to prove the effectiveness of each algorithm. And you can also think to propose your own algorithm, but it needs complete analysis of the existing algorithms, and you have to properly watch the physical phenomenon or the natural phenomenon to relate to the optimization algorithm. So with this, I can stop. If you have any questions, you can ask me, please. Hello, do you have any question?
Excuse me, sir.
Yes, please.
Hello. Sir, Yes, sir. Is there any possibility, sir, to correlate, inculcate all these manufacturing techniques which you have discussed right now, optimization manufacturing techniques, with the computational fluid dynamics? Can we create a synergy between these two?
In fluid dynamics, also you can have multiple objectives or single objectives. You can use in any optimization is common to all the branches. When you need the optimization, you can solve such type of problems. In fact, we have done some work on finding out the friction coefficient in open channel flow. So we have used the predictive models as well as the optimization equations for solving such type of problems. That was published in flow instrumentation, some journal, some 5-6 years back. We have did such type of work. So optimization is quite general to be applied to all branches of engineering and science.
Okay, sir. If required, I will take help of you, sir.
Sure. Don't worry.
Thank you, sir.
Any more question, please? Hello.
Okay, sir. I think no more questions are there from the participant side. So I must conclude the session. So once again, sir, good afternoon to you all, the most valued invited guests, the present excellencies, faculty members, and my dear friends. It's my privilege to have been asked to propose a vote of thanks on this occasion. I, Dr. Rahul Mishra, on behalf of Sri Shankaracharya Technical Campus and Mechanical Engineering Department, and my own behalf, extend a very hearty vote of thanks to Dr. Mahapatra, sir, for gracing your important work and sharing with us your findings and opinions today in 1 week short-term training program in multi-objective optimization methods for engineering and scientific applications sponsored by AICT. I once again thank Dr. Mahapatra, sir, for sharing his knowledge on the topic of different optimization techniques like SOPT, TLBO, PSO, and HS. So basically, the simple optimization technique which have been developed by Hassan Sebi and Azad recently. This technique has been developed recently, and lot many work can be done on this field. So we'll definitely try our level best, sir, and we'll take your help as and when required. Thank you once again, sir.
Thank you very much. Okay. So I'm leaving now. Okay.
Yes, sir. Thank you, sir. Rest all participants, kindly join the next session at